Hello everybody, and welcome to this video on velocity and acceleration. So our objective today is to be able to determine the acceleration of an object from a velocity data table, be able to make displacement, velocity, and acceleration graphs from those data tables. I'd like to begin with you by watching this short little 4-minute video. It's actually a pretty spectacular video. Goes back to that famous Galileo Tower experiment where you drop different objects, and the consensus was that heavier objects fall faster than lighter objects. But when you take out the air drag, watch what happens in this video. So pause it for a second here and click to this YouTube video, and then we'll meet back in 4 minutes to continue on with the video. All right, so after watching the video, let's start with some of the motion equations. And you're going to see this twice. I'll put this in another video too. But here's your basic kinematic motions equations. Some of these you've had already. So speed is distance over time. Velocity is displacement over time. We'll just say delta t, okay? These are when you're moving at a constant speed, all right? So you're not speeding up, you're not slowing down. Now, the acceleration equations are a bit more involved, okay? Our definition of acceleration is this. Acceleration is going to be your final velocity minus your initial velocity over your time interval, delta t, okay? Very often you'll see this equation rearranged into, this is just algebraically rearranging into VF equals VI plus AT. Same equation, just rearranged. So when you're trying to find your final velocity. So the definition of acceleration is your change in velocity over time. Plain old English, here's what it means. If you're speeding up or you're slowing down, you're accelerating, okay? The positive and negative signs are a big element of confusion, so we're going to make sure we clear that up. There's two other kinematic equations that are derived through calculus. We'll talk about the derivation of those later. For now, I'm just going to give you those equations, and it's going to be your displacement, x final minus x initial, equals VIT. That means your initial velocity multiplied by your time plus 1/2 AT squared. If it's a falling object, A is going to be your acceleration due to gravity. And A is always going to be equal to 9.8 meters per second squared if it's a falling object. If it's a jet engine or a car or something, it may be a different acceleration. But if they ever talk about a falling object, you've already got the value for A. Just put in 9.8. Sometimes we use 10 when we're doing examples in class because it's just an easier number to work with. 9.8 is pretty close to 10. Finally, the last equation is this. Your final velocity squared is equal to your initial velocity squared plus 2a, and I sometimes say d for distance, but technically it should be displacement, x final minus x initial. Okay? Sometimes you'll see me write this in shorthand form, vf squared equals vi squared plus 2ad, but when you're writing the full equation, this is how it should be written correctly, okay? So those are our basic kinematic equations. We're going to work with those a lot this unit. You're going to be very comfortable with those. I know right now it looks like a lot of Greek letters, but after you work with them and get the hang of them, it's not too bad, okay? What I'd really like you to gain more from this video is a conceptual, intuitive understanding of acceleration in a graphical form from a data table. So let's take this data for a falling object where the acceleration is equal to g, and in this problem we're just going to let it be 10 meters per second squared. Okay, just to make the math easier, it's easier to conceptualize and see what we're doing here. When you're doing a real problem with a calculator at your desk, you probably want to use 9.8, but for these problems 10 is fine. Okay, so now I'm going to let down be positive on this just to get rid of the negative signs and keep things pretty simplified here. So here's the time interval, 1 second, 2 seconds, 3 seconds. If this is your acceleration, what that means is every second that goes by, your speed is increasing by 10 meters per second. So after 2 seconds, you're now going 20 meters per second. And if you want to know what that is in miles per hour, cut it in half and you're pretty close, okay? So the next one, sorry, excuse me on that one, you want to double that and then you would be pretty close to your miles per hour. So after 3 seconds, you're going to be going 30 miles per hour. Sorry, meters per second. Now I'm confusing myself. And after 4 seconds, you're going 40 meters per second. And you could take this table all the way down, keep going down. Every time you're going to be increasing by 10, 10, 10. Okay, now, what happens in real life? You might have heard of the story of if you drop a penny off the Empire State Building, it would kill somebody because it'd be going so fast. Well, if you put it on this data table and you figure out how many seconds it falls, yeah, you would think that. But what happens is air drag kicks in and this thing hits a top limit number and doesn't increase anymore, and that's called terminal velocity. We'll go into more detail on that later, okay? Now, the distance that it falls, this is a little bit more complicated. You're going to have to think here. Okay, now I could give you the formula, you could plug in the numbers and solve for it, but that doesn't mean you understand what's going on here. Most people want to say, oh, after 1 second, it's gone 10 meters. That's not the case. It started off at 0. After 1 second, it's going 10. Its average velocity for that 1 second interval is 5 meters per second. You take the 10 plus the 0, add them together, divide by 2, and you end up with 5. So its average velocity is 5 meters per second. So after 1 second, it's fallen 5 meters. Okay? Now for the next interval, look at it from here to here. From 1 second to 2 seconds, its average velocity would be, split 10 and 20 in half and you get 15. It would have fallen 15 meters from 1 second to 2 seconds. But it's already fallen 5. So the 15 plus the 5 means that it's fallen 20 meters. Okay? Try the next one. I think you'll start to get the hang of it here. From 2 seconds to 3 seconds, it was going 20 meters per second. Now it's going 30 meters per second. Its average velocity for that interval is 25 meters per second. So it fell 25 meters from the 2 second mark to the 3 second mark. But it's already fallen 20 meters. So the 20 plus the 25 equals 45 meters. That's how far it's fallen after 3 seconds. Okay? Pause the video for a second. Try the last one on your own and see how far it's fallen after 4 seconds. Okay, so you should have come up with, well, between 3 and 4 seconds, that's 35 meters per second. That's the average velocity. So it fell 35 meters from 3 seconds to 4 seconds, plus the 45 equals a total of 80 meters. Okay, and if you look at these numbers, they're increasing exponentially, and that's governed by the equation that I gave you. Displacement equals VIT. Its initial velocity was 0, so this term's going to be gone, plus 1/2 AT squared. Okay, so we can simplify it because that's going to be 0. So take the last value here, put in 4 seconds. You get 1/2. What's the acceleration? 10 meters per second squared. And what's the time? 4 seconds. So that's going to be 16 times 10 is 160. Cut that in half and you get 80. So this equation will get you these numbers, but I would rather you understand how they're derived there. All right, so now what's the shape of this displacement graph going to look like? We're going to do the distance here, and the time is always on the x-axis. So we're graphing this column and this column. So after 1 second, you've gone 5 meters. I'm going to estimate that's right about there. After 2 seconds, you've gone 20 meters. So that's right there. After 3 seconds, you've gone 45 meters. You can see this going up exponentially. It's right about there. And after 4 seconds, you've gone 80 meters. Okay, and as you know, I have a hard time doing graphs on this computer here, but you're going to get something like this. Connect your lines up, and you should get a nice exponential curve. And this equation tells you why it's exponential. See that? That's an exponential curve equation right there that you've learned in algebra. So hopefully your graph looks way better than mine. Definitely not like that, but it is a parabolic shape. So there's a golden rule for you right there. For an accelerating object, the displacement graph will be exponential. Put that in your hard drive. Always remember that. Okay, what about a velocity graph? For the same data table, you may have to flip back and forth here to kind of write that down. Okay, if we were to graph the velocity versus time, after 1 second it's going 10, 2 seconds it's going 20. This is a nice linear graph. 3 seconds 30, 4 seconds 40. So here's the velocity graph for that falling object. It's a nice straight line at a 45-degree angle there. Okay, and that's what that should look like. And then finally, if we flip back here, our acceleration is 10. Every time its velocity increases by 10. This is where people get a little tripped up. the acceleration is a constant 10. It's a horizontal line. Okay? So for a constant accelerating object, that's going to be horizontal. And that's what your three graphs look like for a falling object. Okay, let's try another one here. And it's not for a falling object anywhere. It just gives you some information here. I should have said it's constantly accelerating. You have to fill in the rest of the data table. So pause the video for a second and see if you can figure out what the rest of it's going to look like. Okay, so you come back here, you can see the trend. Every second that goes by, it's increasing by 2 meters per second. So there's going to be 8 meters per second, 10 meters per second, and 12 meters per second. Okay. The distance that it covers, follow the same rule we did last time. So it started off at 0, it ended at 2. Its average velocity for that interval is 1 meter per second. So it will have traveled 1 meter. Okay. From here to here, from 1 second to 2 seconds, its average velocity is 3 meters per second. So it traveled 3 meters from the 1 mark to the 2 mark. But it's already gone 1 meter. So the 3 plus the 1 equals 4 meters that it's traveled. Okay. Over here, its average velocity is going to be 5. Plus it's already traveled 4 meters. So it's going to be 9 meters. Okay. Here its average velocity is 7. Plus the 9, it's going to be 16 meters. You can see these numbers are going up exponentially. And then the last two are going to be 25 and 36 when you work those out. Okay? Why don't you pause the video for a second and try to work these two graphs here and see what these three graphs. I want you to make a displacement graph, a velocity graph, and an acceleration graph. So remember, our displacement graph, you're going to put time on the x-axis and your displacement or distance on the y-axis. Okay, so what's this displacement graph going to look like? It should be exponential. After 1 second, we are 1 meter, so I'm just going to kind of estimate that's going to be right about there. After 2 seconds, we're going to be 4 meters. After 3 seconds, we're 9 meters. And after 4 seconds, we're 16 meters. Yeah, that looks exponential there. Finally, after 5 seconds, we're 25 meters. Okay? You should have a nice parabolic graph like that. So there's your displacement graph. Finally, your velocity graph is going to look like this. After 1 second, you're going 2 meters per second. That's going to look just like the falling rock one, a nice linear line. Straight up like that. And finally, what is our acceleration? Well, every second that goes by, it's increasing by 2, 2, 2, 2. So it's going to be a constant acceleration right at the 2 mark. So it's going to be a horizontal line just like that. That's your acceleration graph. Okay. Finally, I'd like to end with this. And we're going to go into more detail on this later. There's a misconception that sometimes people think anytime you have a negative acceleration, you're slowing down. That's not always the case. You have to look at the direction you're going. So we're going to define this as, okay, if you're moving to the right, you're going east, and that's in a positive direction. If you're moving to the left, just like on a number line, you're traveling west, and that's in a negative direction. So here's a chart that gives you every possible scenario. Positive velocity, positive acceleration. That means you're going to the east and you're speeding up. Okay, you're hitting the gas pedal, driving to the east. If you've got a positive velocity and a negative acceleration, that means you're traveling to the east, but you're slowing down. Okay, if you've got a positive velocity and no acceleration, you're on cruise control. You're not speeding up, you're not slowing down, and you're going east. Okay, these scenarios are the tricky ones. These are the ones that always trip people up. A negative velocity, you're traveling west towards California, and you've got a positive acceleration. That means you're braking as you're traveling west. When you put it in the formula here, let the formula be your guide. Vf squared minus Vi squared over delta t. Okay, that would be a situation if you're braking, your final velocity is less than your initial velocity. So let's say it's going to be 5 and your initial velocity was 8. over some time interval. Okay, and since you're going in the negative direction, both of those are negative. So when you do that, you end up with a, just put some positive time over there. Okay, when you do that, you end up with that turns into a positive, you end up with a positive number. Okay, and then in this situation, you're accelerating and traveling to the west. Okay, I need to devote more time to this. I just want you to have this chart right here. I recommend you write this chart down and have it somewhere so it's a handy access to you, but we're going to spend more time going into detail with this. I think that's enough information for now. We need to break this down and do a little bit of practice with that. So hope you have a good day, and we'll review this a few more times.